We have now talked about solubility in a few different ways. We've talked about trends in solubility. We've talked about saturated, unsaturated. But this section is actually really the meat of this chapter. It's how can we accurately represent the solubility of any solution? Because we talked about unsaturated solutions, but we said, hey, look, if I take 1 crystal of salt versus a tablespoon of salt and dissolve it in the same water, both of those are unsaturated. I could add more salt, but they're different. And so how could we describe that? And so what we're going to run across in this chapter is several different units that we can use to talk about solution concentrations. And each one of the units is used in different scenarios and has its pluses and minuses. So we'll talk about all the different ones and a little bit about when we might want to use those. So our first one here, we talked about solubility of sugar that can dissolve in 100 grams of water. So let's say we took 100 grams of water and 100 grams of water, and we put in I want to start with 80 grams of water, my apologies. 80 grams of water, and I put in 20 grams of sugar, and I wanted to know, what's the percentage of sugar in water? What percent sugar is that, right? You might want to know that if you have a juice concentrate, if you've ever used those frozen ones. That's a concentrated juice. It has a high percentage of sugar. What we usually do is dilute it in order to drink it. But let's figure out what the percent sugar is here. Well, percent of anything is, right, the thing we're talking about over the total times 100%. So what we're going to do is we're going to do grams of sugar, that's the thing we're talking about, over the total grams, and we're going to multiply by 100% in order to figure out our percent sugar. So we've got 20 grams of sugar. We've got what total grams? Well, we have the sugar and the water that we added. So 20 grams plus 80 grams, and then we're going to multiply that by 100% in order to get our answer. If you do that workout, hopefully you get yourself 20%. And so this solution of 20 grams of sugar and 80 grams of water is 20% sugar. Now, it turns out we're going to calculate several different percentages. And so what we want to know is what kind of unit were we using in order to calculate it? Because the units go away as soon as we get the percentage. It doesn't say percent grams or anything like that. So when we report concentration units, we're never going to report them just as percent because that's not sufficient. We're going to report them as percent plus give some information about the units used to calculate it. And the units here were grams and grams, but we don't say grams and grams. We say mass and mass. And so we say m over m. It was a mass divided by a mass. And you'll see why in a little while, because we sometimes do volumes and things like that. So we say that this solution has a concentration of 20% m over m. And in general, how you calculate percent m over m is very similar to what I wrote above. It's the grams of your solute over the total mass. And the total mass is going to be grams of solute plus grams of solution times 100%. Now be careful when you get this 100%. If your calculator has a percent key, don't type that, because what happens when you type the percent key is it divides by 100. You're going to multiply by 100 in your calculator. You're not going to press percent. So on the other one, I did 20 divided by 100 times 100 to get my 20. And that's our generic formula for calculating percent by mass, percent m over m, or percent by mass. Now, it also turns out you don't have to use grams. You could use kilograms as long as you use the same unit on top and on bottom. You can even use pounds if you wanted to, as long as the same unit on top and the same on the bottom, because they cancel out. So let's do an example. What is the mass percent of a solution when 48 grams of potassium fluoride is dissolved in 250 grams of water? So I encourage you to pause and see if you can solve that one. All right. Hopefully you came up with percent m over m is the mass of my solute. It's the thing I have less of. 48 grams of potassium fluoride divided by the total mass. And so it's going to be 48 plus 250 grams times 100%. And if you do that math out, you get 16%. and I can't leave it as just 16%. And we'll see why in a moment, because there's several different units that we're using. I have to say 16% m over m. In general, these kind of problems, whatever sig figs you had in the solute is what you'll have in the answer. Because you're adding at the bottom, you usually end up with either more sig figs or the same sig figs. So that's generally a good idea. Whatever sig figs you had in your solute is what you have in your answer there. So that works well when we're adding a solid to a solid, because we generally measure solids in units of grams, great, because we put them on the scale. But sometimes we have liquids as well. And what are we going to do in case we have a liquid? Well, if I take, for example, 10 milliliters of ethanol, which is alcohol, and I add it to 20 milliliters of water, and I put that into there, I now have a total volume of 20 plus 10 is 30 milliliters, but it's now a mixture of my two things. But everything I'm doing, I'm measuring in volume. So in cases where you're measuring liquids, oftentimes people will use a volume percent. And a volume percent has a very similar definition to our mass percent, and it's going to be the volume of my solute over the total volume. And the total volume is the solute plus the solvent. I think I wrote the wrong thing 2 slides ago. Now I think it. Volume grams of solute plus grams of solvent. Sorry about that. Grams of solute plus grams of solvent back there if you want to fix your notes. All right. Volume of the solute plus the volume of the solvent is the total volume. We times 100% when we do that. And that's what we do for a volume percent. Okay, so how could we do something useful with that? What kind of question would we have when we were talking about that? Let's say we prepared a solution with 12 milliliters of methanol and 125 milliliters of water, and we want to know what is the volume percent in this solution. Well, we're going to solve by typing it into the formula we have above. It's the volume of our solute. Solute's the thing you have less of. 12 milliliters of methanol. Total volume. We're going to put 12 milliliters plus 125 milliliters. Now, it turns out that if you want to be really, really precise, volumes don't add exactly, but we're not going to worry about that in this class. We're going to assume that if you take 2 liquids and combine them together, their volumes add. Times 100%, you plug that in your calculator. You have to be very careful when you plug this in your calculator to use parentheses around the bottom here. You don't want to type 12 divided by 12 plus 125. You're going to get 126. And that's not what you want. We want to do 12 divided by parentheses, 12 plus 125, close parentheses, times 100. And when I do that, I get 8.759124. How many sig figs do I get? In general, I said you're going to get it from there. And so we get 8.8. Now, this is a percent. And what do you think we're going to put at the end of there? We don't leave it as just percent, because now we have our second percent unit already. And so this is going to be percent V over V. We compared a volume to a volume. We did this in milliliters, but it also works for any other volume unit as long as you have the same unit on the top as you have on the bottom. Your turn. What's the concentration of a solution when 43 milliliters of orange juice is added excuse me, to 205 milliliters of water? Go ahead and pause. All right. What did you do? Hopefully you took your 43 milliliters and divided by 43 milliliters plus 205 milliliters times 100% to get yourself 17.34%. But this is V over V, right? We compared a volume to a volume. We only have 2 sig figs, and so we get 17% V over V. But sometimes, and actually a lot of the times, we're taking a solid like salt, sugar, and dissolving it in water. And one of those we measure in mass, and one of those we measure in volume. We could convert between the two, but sometimes it's actually difficult to do unless you have the right data. And so people made another set of units because they can, and they made one called mass to volume percent. And mass to volume percent looks very similar to what we saw in the other ones. It's going to be the grams of our solute over the milliliters of our solution. Right, the solution being the entire thing, the solute and the solvent, but we'll talk about that in just a second, times 100%. One very important thing to notice about this one is it has very specific units here. It's grams and milliliters. These units do not cancel. Grams doesn't cancel milliliters, so technically mass to volume has units at the end, but no one ever includes them. They're just assumed that you know that they are grams and milliliters. While in the other two, the mass to mass, volume to volume, you could use other units, kilograms, milliliters, or liters. It's fine. Here you have to use grams and milliliters very, very specifically. So that is important. And what are we going to do? Always an example is great. We're going to take 18 grams of sugar and dissolve in 100 milliliters of water and find my mass to volume. Okay, how are we going to do that? Well, we're just going to plug into our solution, our equation here. It's going to be the mass of my solute, which was 18 grams of sugar. Milliliters of solution. Well, I've got 100 milliliters of water, but I just added some sugar to it. So what's the new volume? And some people will say, well, you just add 18 to that. But it turns out that's not what happens. It turns out when you dissolve a little bit of sugar into water, the volume doesn't change by much. And in fact, we're actually going to use 100 milliliters as our final volume of water. How can we get away with that? Because there's this general rule that people use that when you add a small amount of solute, and people always ask, what's small? Everything in this class where you're asked to do that is small. Okay, small amount of solute to a liquid, volume doesn't change. And we're going to use that in this class, that the volume doesn't change. And so we're going to assume that at the end we had 100 milliliters of water, because that's what we started with. 18 over 100 times 100% is 18%. And what do you think we're going to use at the end of that unit? We're going to use m over v to say that we calculated this using a mass to volume ratio, not some sort of other ratio like volume to volume or mass to mass. So, what's the best unit? I take a powdery substance, I dissolve it into a liquid. What's the best unit of measurement to describe the concentration of this mixture? And you know, many of you probably came up with B, but B is only the right answer if you happen to have units of mass and volume. If you happen to have units for both of them that are mass and mass, then this is the best one. If you happen to have units that will get you these other things, then something else might be a better way of measuring it. So there actually is no best unit for measuring something. It depends on what units you have available to you and what other people in your field might expect you to do something in. As chemists, we're going to see in just a moment that almost everyone does stuff in molarity. So these other units of m over m, m over v, v over v, very rarely used by chemists, but very commonly used in the health fields. So here's your example. We got a solution prepared by adding 28.58 grams of calcium chloride to 500 milliliters of water. And I want to know the concentration of this solution in mass percent. So pause for a moment. Try that one out. Did you really? Okay. I have to trust you because you're not talking to me. Alrighty. What do I want to do? First thing, when you figure out what it is you want, if there's a definition that goes with it, write that definition down. We know that mass percent is the mass of my solute over the total mass. So I better have a mass of solute and a total mass in order to do this. Mass of solid's easy. I got myself 28.58 grams of calcium chloride. How about my total mass? And some people are going to be very tempted to write this out. I'm going to write it out wrong first. And they say 500 milliliters plus 28.58 grams. And it turns out the math in that case will serve you right. You'll get the right answer mathematically. But the problem is you can't add milliliters and grams. Okay? It's like saying, well, I've got 4 apples and 3 cherries, and please add those together to tell me how many apples I have. You're like, well, you only have 4 apples. I can't add cherries to apples. You're like, no, I want you to add the cherries to the apples, please. Well, you can't, because you can't get apples if you're adding cherries. You have 4 apples. No, please. All right, you can go on forever. That's the same thing about adding different units. You can't do it. So this is not possible. What do I have to do? I have to add the same unit. So somehow I've got to get those milliliters into grams. And hopefully you've heard this enough times. Grams and milliliters, that's density. So 500 milliliters, what is the milliliters of? It's of water. Oh, thank goodness it's water, because what do we know? We know for water that the density is 1.00 grams for every 1 milliliter. It's just a number I expect you to know and be able to use off the top of your head. And so we do get that this is 500 grams of water. And so we can use that equation, but it's going to look like this. That it's 28.58 grams of calcium chloride divided by 500 grams of water plus 28.58 grams of calcium chloride times 100%. And if you do all that one out, what do you get? You get a number that I didn't write down. And so 28.58 divided by 500 plus 28.58 times 100. And I put parentheses around the 500 plus the 28. I forgot to say it out loud. And you get 5.41%. I technically gave myself some 4 sig figs. I'd be okay if you reported this one to 3 or 4. It's technically 3, but we'll give it. We'll let you do 4. What do I put at the end of there? Well, it was an m over m, so I put m over m just like that. 5.41% m over m. That's how we do these kind of problems. Okay. Last unit that we're going to talk about in units of concentration is molarity. Remember how I said in one of my videos a while back that moles were the currency of chemistry. They're what kind of operates underneath everything else. If you want to exchange this for that, we're probably going to do it in moles. And so as a chemist, we want a concentration unit that talks about moles, and that is molarity. And what is molarity? It's very specifically defined as the moles of my solute, remember what I have less of, over the liters of solution, right? That's the total volume in liters. That's it. No percentage here. Notice I did not write a percent here. We do not multiply molarity by 100. It's very important. People get that confused a lot, but you never want to multiply molarity by 100. So let's do a very, very quick and easy example. We're going to take 1.5 moles of salt, and we're going to dissolve in 2.0 liters of water and find the molarity. Okay, 1.5 moles of salt dissolve in 2 liters of water and find the molarity. We'd say molarity is moles of solute. What's my solute? I have less salt. So it's 1.5 moles of salt over liters of solution. What's my solution? It's water plus salt. But remember, in this class, we're going to make the assumption that when we add salt to the water, we're not going to change the volume much. And so it's 2.0 liters. And so we have 1.5 divided by 2.0 is 0.75. And what do we put at the unit? We put a capital M. Right? I'm not very good at my capital letters versus my lowercase letters. Let me really make that a capital M. Capital M for molar. That's how we pronounce it, just like the tooth in the back of your mouth. Molar. So we say this solution has a concentration of 0.75 molar. And that is how we use molarity, no percentages, no other things just like that. So let's find the concentration molarity of a solution when 4.92 grams of magnesium bromide is added to 150 milliliters of water. Now, what is molarity again? Never hurts to write down a definition. Moles of solute, liters of solution. Do we have either one of those? And the answer is no, we don't have either one of those, which means we have a little bit of work to do. First, we have to figure out what's our solute. Is it the magnesium bromide or the water? You're like, well, 150 milliliters of water is a lot of water compared to 5 grams of magnesium bromide. So chances are magnesium bromide is my solute. So somehow I've got to get this 4.92 grams of magnesium bromide into moles. How do I get grams to moles? Grams to moles. Hopefully that jogs something in your brain. That's from my periodic table. But even more important, I got to figure out what is magnesium bromide. It's very tempting just to write down MgBr because you're like, well, that's magnesium and that's bromine. Great. But you have to remember, everybody has a charge. Magnesium's a +2, bromine's a -1. Does +2 and -1 balance out? Absolutely not. I need 2 of the minuses. And so I do it like that, MgBr2. And so I've got to go to the periodic table and figure that out. When I do that, I've got that magnesium is 24.31 grams per mole. Bromine is 79.90 grams per mole. But I've got 2 of them, so I have to multiply by 2. And when I add those all together in my calculator, I get 24.31 plus 79.90 times 2. I get 184.11 grams per mole. So I first have to take that 4.92 grams of magnesium bromide, 4.92 grams of magnesium bromide, and convert that to moles. If I'm converting that to moles, my grams has to go down here. My moles has to go up here. Now, where does that 184.11 go? It's attached to grams, so it's got to stay down here. So it's 184.11 in 1 mole. I multiply that out. 4.92 divided by that 184 is going to be 0.0267 moles of MgBr2. Okay. So I've got moles now, but what do I need? I need liters of solution. Oh man, so much work. Okay, how do I get liters of solution? Well, I've got milliliters, so I just need to convert those milliliters to liters. I've got 150 milliliters of water. I want to convert to liters of water. What's got to go on the bottom? Milliliters. On the top, liters, because these two have to cancel. This one's got to get me what I want. What's my relationship between liters and milliliters? It is 1,000. Lots of little milliliters in 1 liter, and I get 0.150 liters of water. Now I'm finally ready to plug that into my molarity equation, which is moles of solute, 0.0267 moles of MgBr2 versus 0.150 liters of solution. And I can plug that in my calculator. And 0.0267 divided by 0.150 gets me 0.178, and I get molar. My sig figs get a little complicated with all these numbers, but if you're going to try to guess at something, look back up at what you started with. I started off with 2 different numbers. 3 sig figs here, 3 sig figs here because of that decimal. So chances are my answer is going to have 3 sig figs, which it does, 0.178 molar. Whew, lots of steps to that one, lots of things to keep track of. But what did I do? I started off by writing out this definition. It was a really important step because it guided the rest of what I did. It said, I need moles of solute. How do I get that? I need liters of solution. How do I get that? Just looking at that problem statement, you might not have come up with the same steps as you did by writing down that definition. Okay. So it's a very important step in clarifying how to solve problems. Write down definitions, write down formulas. They help guide you in your work. Alrighty. Our last example, I believe, is we are going to take one solution where we take 45 grams of sodium chloride, dissolve in 475 milliliters of water, and find the concentration of molarity, m over v, and m over m of the same solution. So you can see that those numbers are actually a little bit different. We're going to assume the total volume doesn't change when the salt dissolves, which is what we're always going to do in this class. Adding a solid to a liquid, we're going to assume the volume doesn't change. So what's the easiest one? Well, we've got grams here and we've got milliliters here, so the easiest one is going to be mass to volume. And so it's going to be 45 grams of my solute divided by 475 milliliters of my solution times 100%. If you do that one, you get 9.5%. Do I just leave it like that? No, I've got to write the m over v to tell people that I did a mass to volume ratio problem. The next easiest one, well, how am I going to get m over m? How do I get a mass from my milliliters? How do I get to grams from milliliters? All right, it's density again, 475 milliliters of H2O. I know the density off the top of my head as 1.0 gram per milliliter. And so I get 475 grams of H2O. So if I'm doing my mass to mass, I get the following. I get mass of my solute over the total mass. Now here's where things get a little bit different. The total mass is my solute plus my solvent, whereas when I was doing the one above, it was just the solute because we said that, hey, the solvent, because we said that, hey, the volume's not going to change much, so the solvent volume is our final volume. But that's not the case here. And so we get our mass to mass looks like this one. If we do the math out, we get 8.7%. Can't just leave it as percent. We've got to tell people that this is a m over m. And so you can see the same solution has a different mass to volume percent than a mass to mass percent. So it's important to know which one we're talking about, which is why we always include this after our percent unit. Molarity a little harder, right? Never hurts to write out a definition. Molarity, moles of solute, liters of solution. How do we get each one of those? Moles. Our solute here is the sodium chloride. We've got 45 grams of sodium chloride. We want to convert that to moles of sodium chloride. Moles is going to go up on top, grams on bottom, so it can cancel. What's our relationship between moles and grams? Moles and grams. Moles and grams should take you back to the periodic table, and you just find our 22.99 for sodium, our 35.45 for chloride. That's in 1 mole. You do that workout, you get 0.770 moles of sodium chloride. Now you can put that into your molarity equation. 0.770 moles, liters of solution. Let me look back up. I only have milliliters of solution. We showed the milliliters to liters conversion in a different problem, so I'm not going to do it again. But you do need to do that milliliters to liters conversion, because this one has to be in liters. If you do it in milliliters, you're going to get wrong answers. So I've got divided by 0.475 liters, no percentage. This is just a straightforward calculation. And I get 1.6 molar. 2 sig figs, because I started with 2 sig figs. The reason I put 3 sig figs in this answer is it's not my final answer. And we're making intermediate calculations, calculations that aren't your final answer. It's actually a good idea to leave yourself 1 or 2 extra sig figs so you don't end up with rounding errors. So that's just fine because it's not my final answer. I don't have to worry too much about the sig figs on it as long as I have extra. Excuse me. So I get 1.6 molar, I get 8.7% m over m, and I get 9.5% m over v. And that is our discussion of the units of molarity. And we now know mass to mass, mass to volume, volume to volume, and molarity. And in the next section, what we're going to do is use those as conversion factors. I knew you were just waiting for it, weren't you? But that's what we're going to do. Thanks.